You're floating in the vastness of space, weightless, surrounded by an endless sea of stars. Most are modest, twinkling quietly like distant fireflies. But then, your gaze locks onto something else. A monstrous, blazing giant that dominates the cosmic skyline. It's a star so massive, so luminous, it could outshine 1,000,000 suns combined. Its surface churns with fiery plasma, pulsing like a cosmic heart ready to burst. These are the monster stars, the universe's most dangerous titans. And they're not just beautiful. They're deadly. What makes these stars so special? And why should you care? Let's dive into the heart of these cosmic beasts and find out. But first, quick question. What do you think makes a star a monster? Drop your thoughts in the comments and let's see if you're onto something as we unravel this mystery together. Picture this. You're staring at a star so massive it could swallow our sun 1,000 times over. These aren't your average backyard stars you spot on a clear night. Monster stars, or hypergiant stars, are the rarest and most extreme stellar objects in the universe. They're the heavyweights, packing millions of times the energy output of our sun. Take a star like VY Canis Majoris. It's so big that if you plopped it in the center of our solar system, its edges would stretch past Jupiter's orbit. That's not just big, it's mind-bogglingly enormous. You'd need a spaceship cruising at light speed for hours just to circle it once. And it's not just their size that's intimidating. These stars burn so fiercely that they live fast and die young, often in catastrophic explosions that reshape entire regions of space. Why are they so dangerous? It's all about their raw power. These stars are like cosmic pressure cookers, fusing elements at their cores with such intensity that they're always on the brink of collapse. Their surfaces are chaotic, with massive eruptions flinging material into space at speeds that make a bullet look sluggish. Imagine standing on a planet near one of these beasts. Spoiler alert, you wouldn't. The radiation alone would fry you faster than a marshmallow in a microwave. And here's a little cosmic humor for you. If a monster star were a chef, its signature dish would be planetary barbecue with a side of annihilation. Not exactly Michelin star worthy, but it gets the job done. Let's ground this in something tangible. You know the sun, right? It's been shining for about 4.6 billion years and will keep going for another 5 billion or so. Monster stars? They're lucky to last a few million years. Their massive size means they burn through their fuel like a sports car guzzling gas on a racetrack. This short lifespan is what makes them so rare. In our Milky Way, there are maybe a few dozen true hypergiants among billions of stars. Finding one is like spotting a unicorn in a haystack, but when you do, it's unforgettable. Their light can travel across the universe, reaching telescopes on Earth and giving astronomers a front-row seat to their cosmic drama. Now, let's sprinkle in a bit of history. Back in the 19th century, astronomers like William Herschel were already noticing stars that seemed impossibly bright and massive. Herschel, peering through his telescope, cataloged thousands of stars, but he couldn't fully grasp the scale of these monsters. It wasn't until modern spectroscopy, using light to decode a star's composition, that we began to understand their true nature. These tools revealed that monster stars aren't just big. They're chemically complex, forging heavier elements like iron in their cores, which sets the stage for their explosive deaths. Here's a quirky detail you probably didn't expect. Some monster stars are so unstable they literally burp out chunks of themselves. Take Eta Carinae, a famous hypergiant that, in the 1840s, had a massive outburst astronomers call the Great Eruption. It ejected a cloud of gas so huge it formed a glowing nebula, visible from Earth. Imagine a star throwing a tantrum so epic it creates its own cosmic fog. This instability is part of what makes these stars so fascinating. They're not just sitting there shining. They're actively reshaping their surroundings, spitting out material that could one day form new stars or planets. But let's pause for a moment of debate. Astronomers still argue over what exactly qualifies a star as a hypergiant. Is it just about size, or is it about mass, luminosity, or instability? Some say a star needs to be at least 100 times the Sun's mass, while others focus on its spectral type, a kind of cosmic fingerprint. This open question keeps researchers up at night, poring over data from telescopes like Hubble and the James Webb. It's a reminder that even in a field as old as astronomy, there's still so much we're piecing together. Feel the weight of this for a second. You're looking at a star that's a ticking time bomb. Its core is a furnace, fusing hydrogen, helium, and heavier elements at a breakneck pace. Every second, it's inching closer to its doom, and when it goes, it won't go quietly. The energy released in its death could outshine an entire galaxy for weeks. That's the kind of power we're talking about. Power that can forge new elements, scatter them across space, and even influence whether life can exist nearby. These stars are the universe's ultimate creators and destroyers, sculpting the cosmos with their fiery tempers. Now, imagine zooming in closer. You're not just seeing a star, you're witnessing a cosmic titan at work. Its surface is a roiling ocean of plasma, with magnetic fields twisting and snapping like cosmic lightning. Flares erupt, sending waves of radiation into the void. It's beautiful, but it's also terrifying. If you were a space explorer, you'd want to keep your distance, say a few light years. And here's a modern twist. Today's astronomers use supercomputers to simulate these stars, modeling their chaotic lives in stunning detail. It's like watching a cosmic blockbuster, but instead of CGI, it's pure physics. So, what's the takeaway? Monster stars are the universe's rock stars. Brilliant, short-lived, and dangerously unpredictable. They're not just objects in the sky, they're forces of nature, shaping the cosmos in ways we're only beginning to understand. As you ponder their scale, think about this. Our own sun is a middle-class citizen of the galaxy. But these hypergiants? They're the royalty, the rebels, the ones that break all the rules. And their story is just getting started. Before we move on, let's have a bit of fun. If you could name a monster star, what would you call it? Something epic like Doom Flare, or maybe something cheeky like Big Blinky. Share your ideas below, and let's keep this cosmic adventure rolling. In the next part, we'll rewind the clock to see how these giants are born from chaos itself. Stay curious. You're drifting through a cosmic nursery, a vast cloud of gas and dust stretching across light years. It's cold, dark, and eerily quiet, like a foggy forest before dawn. But something's stirring. Deep within this nebula, a spark ignites, and the chaos begins. Gravity pulls, gas swirls, and temperatures soar. You're witnessing the birth of a monster star, a hypergiant destined to become one of the universe's most fearsome titans. How does a cloud of scattered particles transform into a blazing colossus? Let's dive into the turbulent, fiery process that creates these cosmic giants and uncover the secrets of their origin. Imagine a molecular cloud, a gargantuan soup of hydrogen, helium, and traces of heavier elements. It's not just any cloud. It's massive, millions of times the mass of our sun, and denser than the emptiest voids of space. You can almost feel the chill, with temperatures hovering near absolute zero. But don't let the calm fool you. This cloud is a powder keg, waiting for the right trigger. Maybe a nearby star explodes, sending shock waves rippling through the nebula. Or perhaps two clouds collide, like cosmic bumper cars. Whatever the spark, gravity takes over, and the cloud begins to collapse. It's like watching a house of cards fall. But instead of cards, it's the raw stuff of stars. As the cloud contracts, you'd see it spin faster, like a figure skater pulling in their arms. This is no gentle process. The core of the cloud heats up, reaching millions of degrees. You'd feel the pressure building, the particles slamming into each other with ferocious energy. It's chaotic, like a mosh pit at a cosmic concert. And here's a little joke to lighten the mood. Why did the nebula throw a party? Because it was ready to collapse into something. Stellar. Okay, back to the action. The core keeps compressing until it hits a critical point. Temperatures hot enough to ignite nuclear fusion. Hydrogen atoms smash together, forming helium and releasing a flood of energy. Boom! A star is born. But not all stars become monsters. Most settle into quiet lives as dwarfs or medium-sized stars like our sun. Monster stars, though, come from the biggest, densest clouds. Regions so packed with material that the newborn star balloons to hundreds of times the sun's mass. These are the overachievers of the stellar world, gobbling up gas like a kid at a candy store. Picture yourself watching this newborn giant, its surface glowing red-hot, already unstable as it struggles to hold itself together. It's not just forming, it's fighting to exist. Its own gravity threatening to crush it from the start. Let's add a historical touch. In the early 20th century, astronomers like Annie Jump Cannon studied star formation by classifying stars based on their spectra. Her work helped lay the foundation for understanding how stars are born, though she couldn't have imagined the scale of hypergiants. Her catalogs, filled with thousands of stars, hinted at the diversity of stellar nurseries. But it took decades of research to piece together the full story. Today, telescopes like ALMA in Chile let us peer into these nurseries, capturing images of collapsing clouds in stunning detail. It's like having a front row seat to creation itself. Here's a quirky fact. Some of these stellar nurseries are so dense they form not just one star, but entire clusters, like a cosmic litter of puppies. In regions like the Tarantula Nebula, monster stars are born alongside hundreds of siblings, all vying for material. Some get kicked out, flung into space like cosmic runaways, while others grow into hypergiants. It's a brutal, competitive environment, and only the biggest survive to become the monsters we're talking about. This cosmic sibling rivalry shapes entire galaxies, creating pockets of intense star formation that light up the universe. Now, let's stir the pot with a scholarly debate. Astronomers still puzzle over the upper limit of a star's mass. Can a star grow to 200, 300, or even 500 times the sun's mass? Or does gravity cap their size? Some models suggest that intense radiation from a forming star can blow away its own building blocks, limiting growth. Others argue that in extreme conditions, like the dense hearts of ancient galaxies, stars could grow even larger. This question drives researchers to scour the cosmos, hunting for the biggest, baddest stars to test their theories. Feel the drama of this moment. You're watching a monster star take shape, its light piercing the nebula's veil. The surrounding gas glows, ionized by the star's intense radiation, creating a bubble of plasma that pulses like a cosmic heartbeat. It's beautiful, but it's also violent. The star's magnetic fields twist and snap, sending jets of material shooting into space. These jets can stretch for light years, carving tunnels through the nebula. If you were close enough, you'd hear nothing. No sound travels in space. But you'd feel the raw energy, like standing too close to a rocket launch. In today's world, we're not just observing this process, we're simulating it. Supercomputers crunch numbers to model collapsing clouds, showing how turbulence and magnetic fields shape a star's birth. It's like a video game, but instead of dragons, you're battling the laws of physics. These simulations reveal that monster stars need specific conditions: high density, low metallicity, and a touch of chaos to form. They're not just accidents. They're the universe's way of flexing its creative muscles, crafting giants that will dominate their galaxies. As the star stabilizes, it begins its short, wild life. Unlike our sun, which burns steadily, a monster star is a cosmic firecracker, blazing through its fuel in a few million years. Its birth is just the beginning of a saga that ends in catastrophe. But for now, you're in awe, watching this newborn titan assert its dominance. Its light is so intense it could blind you from a light year away, and its gravity warps the space around it. You're not just seeing a star, you're seeing a force of nature, born from chaos and ready to reshape the cosmos. One last chuckle. If monster stars had a dating profile, it'd read, "Love's long walks through nebulae, burning bright and going out with a bang." Too bad their relationships with nearby planets don't last long. They're a bit too hot to handle. As we move forward, we'll explore what happens when these stars reach the end of their lives. Spoiler, it's explosive. Keep your curiosity burning, and let's see what these cosmic titans do next. You're hovering in the void, staring at a monster star in its final moments. Its surface churns, a roiling cauldron of plasma, glowing with an intensity that blinds even from light years away. Suddenly, it erupts. A flash so bright it outshines an entire galaxy. This is no ordinary star death, it's a supernova, a cosmic explosion so powerful it could erase worlds. What happens when a monster star goes supernova? And why is it one of the universe's most destructive events? Let's plunge into the heart of this cataclysm and uncover the forces that make these stellar giants the ultimate agents of chaos. Picture the scene. A hypergiant star, hundreds of times more massive than our sun, has burned through its fuel in a cosmic blink. Just a few million years. Its core, once a furnace fusing hydrogen into helium, then helium into heavier elements like carbon and oxygen, is now a ticking bomb. The star's been cooking up iron, and here's the problem. Fusing iron doesn't release energy. It absorbs it. The core can't hold up against its own crushing gravity anymore. You'd feel the tension, like a rubber band stretched to its limit, ready to snap. In a fraction of a second, the core collapses, compressing to the size of a city. The outer layers crash inward, then rebound in a shockwave that tears the star apart. Boom! The supernova unleashes a burst of energy equivalent to billions of suns. This explosion isn't just loud and bright, it's a cosmic wrecking ball. The shockwave blasts outward, obliterating anything in its path. If a planet were nearby, say a few light years away, it'd be scorched. Its atmosphere stripped away, like tissue paper in a hurricane. The radiation from the blast could sterilize entire star systems, wiping out any chance of life. And here's a little cosmic humor to ease the tension. If a supernova were a party, it'd be the kind where the guest of honor trashes the place and leaves everyone glowing. Literally. Not exactly the vibe you'd want at your next birthday bash. Let's ground this in scale. A single supernova can release as much energy in a few weeks as our sun will emit over its entire 10 billion year lifetime. The light from these explosions can be seen across billions of light years, making them some of the brightest beacons in the universe. Astronomers use them as standard candles to measure cosmic distances because their brightness is so predictable. Imagine that. You're watching an explosion so massive, it helps us map the universe. It's like using a nuclear blast to measure your backyard. For a historical touch, let's rewind to 1054 AD. Chinese astronomers recorded a guest star in the sky, so bright it was visible during the day for weeks. This was the Crab Nebula supernova, the remnants of a massive star's explosive death. Today we still study its glowing debris, a testament to the enduring power of these events. Back then, people had no idea they were witnessing a cosmic catastrophe. But their records helped modern astronomers piece together the puzzle of stellar evolution. Now, here's a quirky detail. Supernovae don't just destroy, they create. The explosion scatters heavy elements like gold, silver, and uranium into space. Every atom of gold in your jewelry? It was forged in the heart of a dying star, blasted out by a supernova. Next time you wear a ring, you're sporting a piece of cosmic history. It's a strange thought, isn't it? These monster stars, in their death throes, seed the universe with the building blocks of planets, and maybe even life. They're the ultimate recyclers, turning their own destruction into raw material for the next generation of stars. But let's stir up a scholarly debate. Not all monster stars end in a supernova. Some might collapse directly into black holes without a bang. Astronomers argue over what determines a star's fate. Is it just mass, or do factors like rotation and magnetic fields play a role? Some models suggest that stars above a certain mass, say 150 times the Sun's, might skip the supernova phase entirely, imploding silently into a black hole. Others insist that even these giants produce a blast, just a weirder one, like a pair instability supernova, that tears the star apart in a unique way. This debate keeps telescopes pointed at the sky, hunting for clues. Feel the raw power of this moment. You're watching the supernova unfold, a wave of light and matter rippling across space. The blast sends shockwaves through nearby gas clouds, triggering new star formation. It's a paradox. Destruction sparking creation. The radiation, a deadly mix of gamma rays and X-rays, streams outward, carrying the star's final message across the cosmos. If you were a space traveler, you'd want to be far, far away. Think thousands of light years, minimum. Even then, you'd feel the awe, the sense that you're witnessing something fundamental to the universe's story. In today's world, we study supernovae with cutting-edge tech. Telescopes like the Vera C. Rubin Observatory scan the sky for these fleeting explosions, capturing data that helps us understand the universe's expansion. Supercomputers simulate the chaotic physics of a star's collapse, showing how shock waves ripple and elements form. It's like watching a cosmic crime scene unfold, with astronomers as detectives piecing together the evidence. These tools reveal that supernovae from monster stars aren't just random events. They shape galaxies, carving out bubbles of hot gas and spreading heavy elements that make planets possible. As the supernova's light fades, you're left with a sense of scale that's hard to grasp. This single event can outshine a galaxy of 100 billion stars. Its remnants, like a neutron star or black hole, linger as cosmic scars, bending space and time. And here's a modern twist. Supernovae are so bright they're used to test theories about dark energy, the mysterious force driving the universe's expansion. Every explosion is a data point, helping us unravel the cosmos's biggest mysteries. One last chuckle. If a supernova were a movie, It'd be the ultimate blockbuster. No sequel, just one epic, universe-shaking finale. As we move forward, we'll explore what happens after the explosion, when these monster stars leave behind something even stranger. Black holes. Keep your curiosity ignited, and let's see what these cosmic titans leave in their wake. You're floating in the aftermath of a supernova, the wreckage of a monster star scattered across space. The light has faded, but something ominous remains. A dark, invisible presence warping the fabric of reality itself. This is a black hole, the final legacy of a hypergiant star's violent death. It's not just a void. It's a cosmic trap, devouring light, matter, and even time. Could these mysterious objects be portals to another reality? Or are they the universe's ultimate prisons? Let's venture to the edge of these enigmatic remnants and explore the secrets they hold. Imagine the scene. The monster star, once a blazing titan, has collapsed under its own immense gravity. Its core, crushed to unimaginable densities, forms a black hole, a region where gravity is so intense that nothing, not even light, can escape. You'd feel the pull like a cosmic undertow dragging you toward oblivion. The black hole's event horizon, the point of no return, looms like an invisible wall. Cross it, and you're gone, stretched and compressed in a process scientists call, rather unromantically, spaghettification. Not exactly a fun ride, but it's a vivid reminder of the black hole's power. Let's break it down. A monster star with a mass 100 times that of our sun often leaves behind a black hole weighing 20 to 50 solar masses. That's a lot of matter packed into a space smaller than a city. Picture squeezing the entire Earth into a thimble. That's the kind of density we're talking about. The black hole warps space-time, bending light from distant stars into eerie arcs called gravitational lenses. If you were close enough, you'd see the universe distorted, like looking through a cosmic funhouse mirror. And here's a little joke to keep things light. Why did the black hole go to therapy? It had too many deep-rooted issues from its explosive past. The stakes are high. A black hole from a monster star can disrupt entire star systems. Nearby planets or stars get slung into chaotic orbits or swallowed whole. The black hole's gravity tugs at gas clouds, forming a glowing accretion disk that spirals inward, heating up to millions of degrees and emitting X-rays detectable across the galaxy. It's a violent, dynamic process, like a cosmic whirlpool draining the universe. If you were observing from a safe distance, say a few light years, you'd be mesmerized by the disk's glow, a stark contrast to the black hole's dark heart. For a historical touch, let's go back to 1915, when Albert Einstein published his theory of general relativity. His equations predicted black holes, though he wasn't sure they could exist in reality. It took decades for astronomers to confirm them, using observations of X-ray emissions and gravitational effects. Today, we've even captured images of black holes, like the one in the galaxy M87, thanks to the Event Horizon Telescope. That blurry orange ring from 2019? It's not just a photo. It's proof of the monster star's ultimate legacy. Here's a quirky fact. Some black holes spin so fast they drag space-time along with them, a phenomenon called frame dragging. It's like the universe itself is being twisted around the black hole's axis. This spin can create powerful jets of plasma, shooting out at nearly light speed, stretching thousands of light years. These jets are like cosmic lighthouses, visible to telescopes on Earth, and they hint at the black hole's chaotic birth from a monster star's collapse. It's a reminder that even in death, these stars leave a mark that reshapes the cosmos. Now, let's spark a scholarly debate. Are black holes just cosmic dead ends? Or could they be gateways to other universes? Some physicists, like Stephen Hawking, argued that black holes might slowly evaporate through a process called Hawking radiation, leaking energy over billions of years. Others speculate that the singularity at a black hole's core, a point of infinite density, might connect to a white hole in another universe, spitting out matter. This idea, while tantalizing, remains unproven, fueling heated discussions at conferences and in academic papers. It's the kind of question that keeps theorists staring at chalkboards, scribbling equations late into the night. Feel the weight of this moment. You're gazing at a black hole, its event horizon a sharp boundary between the known and the unknowable. Time slows as you approach, a bizarre effect of relativity that makes seconds stretch into eternity. The accretion disk swirls, glowing with the remnants of devoured stars and gas. You'd sense the danger, the pull of a force so strong it rewrites the rules of physics. If you were an explorer, you'd need nerves of steel and a really good spaceship to get anywhere near this beast. In today's world, we study black holes with cutting-edge tools. Gravitational wave detectors like LIGO catch the ripples in space-time when black holes collide, a phenomenon first detected in 2015. These waves are echoes of monster stars' deaths, carrying clues about their mass and spin. Meanwhile, simulations on supercomputers model how black holes form and grow, showing the chaotic collapse of a star's core. It's like watching a cosmic autopsy, revealing the inner workings of these mysterious objects. Social media buzzes when new discoveries drop, with astronomers and fans alike geeking out over each breakthrough. The black hole isn't just a destroyer, it's a sculptor. Its gravity shapes nearby star clusters, influences galaxy formation, and even regulates star birth by heating gas clouds. In a way, the monster star's legacy lives on, its black hole anchoring the cosmos like a dark cornerstone. But there's a haunting beauty here, too. The contrast between the glowing accretion disk and the black hole's darkness is a visual poem, a reminder of the universe's duality, creation and destruction, light and shadow. One last chuckle. If a black hole were a chef, its signature dish would be spaghettified star soup, not on any menu you'd want to try. As we move forward, we'll explore an even deadlier aspect of monster stars, the gamma-ray bursts that can wipe out life in an instant. Keep your curiosity alive, and let's see what other dangers these cosmic titans unleash. You're standing on a distant planet, gazing at the night sky. A star flickers, then unleashes a beam of light so intense it slices through the cosmos like a laser. This isn't just any light. It's a gamma-ray burst, the most powerful explosion in the universe, born from the death of a monster star. In seconds, it could sterilize entire worlds, stripping away atmospheres and erasing life. Is Earth in the crosshairs of these cosmic death rays? Let's dive into the terrifying world of gamma-ray bursts and find out why they're the ultimate weapons of the universe. Picture the aftermath of a monster star's collapse. Most hypergiants end in a supernova, but the most massive ones, those over 150 times the sun's mass, can go out with an even bigger bang. When their cores collapse, they don't just form a black hole. They channel their energy into two narrow, ultra-powerful jets of gamma rays, shooting out at nearly the speed of light. These beams are so focused they could hit a planet light years away with pinpoint accuracy. If you were watching from a nearby star system, you'd see a blinding flash, brighter than a billion suns, lasting just seconds but packing enough punch to rewrite the fate of anything in its path. Feel the stakes. A gamma ray burst releases more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. If one hit Earth directly, it could strip away our ozone layer, exposing life to deadly solar radiation. DNA would break down, ecosystems would collapse, and mass extinctions could follow. It's like the universe's version of a cosmic sniper rifle, precise, lethal, and utterly indifferent. And here's a little joke to keep things from getting too grim. Why don't gamma ray bursts ever miss their target? Because they've got the best aim in the galaxy. No scope needed. Let's put this in perspective. Gamma ray bursts are rare, happening maybe once every million years in a galaxy like ours. But when they do, they're catastrophic. Astronomers estimate that a burst within 6,000 light-years of Earth could cause serious damage. The energy travels in a narrow cone, so it's like dodging a bullet. Most planets are safe unless they're directly in the line of fire. But the sheer power is staggering. A single burst can outshine every star in the universe combined, making it visible across billions of light-years. It's a cosmic flare, screaming, "Look at me," before fading into darkness. For a historical touch, let's go back to 1967. During the Cold War, U.S. satellites detected mysterious bursts of gamma rays from space. At first, scientists thought they might be signs of secret Soviet nuclear tests. It wasn't until years later that they realized these were cosmic events, coming from distant dying stars. This discovery opened a new field of astronomy, with telescopes like NASA's Swift and Fermi now dedicated to catching these fleeting bursts. It's a reminder of how even our fears of war led to cosmic revelations. Here's a quirky detail. Gamma ray bursts don't just happen in a vacuum. They leave scars. When a burst's energy slams into interstellar gas, it creates an afterglow that glows in X-rays, visible light, and radio waves for days or weeks. This afterglow is like a cosmic crime scene, giving astronomers clues about the star's death and the black hole it left behind. Some bursts are so powerful they ionize entire regions of space, creating bubbles of hot plasma that linger for millennia. It's as if the universe is still reeling from the shock long after the burst has faded. Now, let's spark a scholarly debate. What triggers a gamma ray burst? The leading theory says it's the rapid spin of a collapsing star, channeling energy into jets as it forms a black hole. But some argue that magnetic fields or interactions with a companion star could play a bigger role. Others wonder if certain bursts come from exotic events, like neutron star collisions rather than monster stars. This uncertainty drives astronomers to point their telescopes at every burst, hoping to catch the next clue. It's a cosmic puzzle with stakes as high as life itself. Feel the tension. You're watching a gamma ray burst unfold, a beam of destruction slicing through space. The light is blinding, a mix of high-energy photons that could pierce through steel. If you were on a planet in its path, you'd have no warning, just a flash, then chaos. The atmosphere would heat up, glowing with auroras as radiation tore through it. From a safe distance, it's awe-inspiring, like watching a thunderstorm from orbit. But up close, it's the end of the world. Today, we hunt these bursts with cutting-edge tech. Satellites scan the sky, alerting telescopes within seconds of a burst's detection. Astronomers race to analyze the afterglow, piecing together the star's mass, spin, and environment. Social media lights up with each discovery as space nerds and scientists alike share images of glowing remnants. It's a global effort, like a cosmic scavenger hunt, with each burst offering a glimpse into the universe's most violent moments. Simulations on supercomputers model these events, showing how jets form and why they're so deadly. It's science at its most thrilling, blending raw data with existential questions. The bigger picture is sobering. Gamma-ray bursts remind us how fragile life is. A single misaimed burst could reset Earth's biosphere, wiping out complex life in an instant. Yet they're also part of the cosmic cycle, clearing space for new stars and planets to form. Monster stars, even in their deaths, shape the universe's story. Could a burst hit us? Probably not anytime soon. The odds are low, and our galaxy's bursts are rare. But the possibility lingers, a cosmic sword of Damocles. One last chuckle. If a gamma-ray burst were a text message, it'd be the universe saying, "Oops, my bad," and then ghosting you forever. As we move on, we'll meet some of the most famous monster stars, like Eta Carinae and Betelgeuse, and see what they tell us about the cosmos. Keep your eyes on the stars, and let's keep exploring. You're gazing across the galaxy, your eyes locked on a star that pulses with a menacing glow. It's not just any star. It's a cosmic celebrity, a monster star like Eta Carinae or Betelgeuse, known for their size, instability, and impending doom. These stellar icons aren't just points of light. They're legends, each telling a story about the universe's past, present, and future. What makes these stars so famous? And what secrets do they reveal about the cosmos? Let's meet these celestial superstars and uncover why they captivate astronomers and stargazers alike. Picture Eta Carinae, a hypergiant in the Carinae constellation, about 7,500 light-years from Earth. It's a beast, shining 1,000,000 times brighter than our sun, and so massive it could swallow our entire solar system. Its surface is a chaotic mess, erupting with massive outbursts that make it look like a cosmic volcano. You'd feel the tension just looking at it, knowing it's teetering on the edge of destruction. Eta Carinae's most famous moment came in the 1840s during its great eruption, when it briefly became one of the brightest stars in the sky. The outburst ejected a nebula, called the homunculus, that's still expanding today, glowing like a cosmic hourglass. Now, shift your gaze to Betelgeuse, the red supergiant in Orion's shoulder. It's closer, just 600 light-years away, and massive enough to stretch past Jupiter if it replaced our sun. Betelgeuse has been acting strange lately, dimming dramatically in 2019 and 2020, sparking rumors it might explode soon. Spoiler, it probably won't for thousands of years, but the buzz got everyone talking. Imagine watching this star flicker, its reddish hue pulsing like a warning light. It's like the universe's own drama queen, keeping us guessing about its next move. And here's a little cosmic humor. Why did Betelgeuse throw a tantrum? It was tired of being the second brightest in Orion's constellation. Let's zoom out for context. These stars are rare. Only a handful of true hypergiants and supergiants exist in our Milky Way. Their fame comes from their extreme nature, massive, unstable, and destined for spectacular ends. Eta Carinae, for instance, is actually a binary system, with two massive stars orbiting each other, adding to its volatility. Betelgeuse, meanwhile, is a solo act, but its size and variability make it a favorite for telescopes. Both stars are studied intensely because they're like cosmic labs, revealing how massive stars live, die, and shape their surroundings. For a historical touch, consider the 19th century astronomers who first noticed these stars' odd behavior. John Herschel, son of William, observed Eta Carinae during its great eruption from South Africa, meticulously recording its brightness. His notes helped later scientists understand that this wasn't just a star, but a hypergiant on the brink. Back then, without modern telescopes, these observations were groundbreaking, relying on little more than sharp eyes and patience. Today, we use tools like the Hubble and James Webb Space Telescopes to study these stars in exquisite detail. capturing their spectra and imaging their surrounding nebulae. Here's a quirky fact. Betelgeuse is so big that in 1996, astronomers using the Hubble Space Telescope captured the first direct image of a star's surface, its disk, not just a point of light. They saw a massive, mottled surface with hot spots the size of planets. It's like getting a close-up of a cosmic pizza, complete with bubbling cheese. This was a big deal, proving we could study a star's surface despite its distance. For Eta Carinae, its nebula is so detailed that astronomers can track its expansion year by year, like watching a slow-motion explosion frozen in time. Now, let's stir a scholarly debate. Are these famous monster stars typical of their kind? Or are they outliers? Eta Carinae's binary nature makes it unusual. Most hypergiants are single stars. Some argue its companion star triggers its outbursts, while others say its sheer mass is enough. Betelgeuse's dimming, meanwhile, sparked theories ranging from dust clouds to internal convulsions. These questions drive research, with astronomers debating whether these stars represent the norm or the extreme. It's a puzzle that keeps observatories busy, as each new observation adds a piece to the cosmic picture. Feel the awe of these stars. You're watching Eta Carinae's nebula glow, its twin lobes lit by the star's ferocious output. The light you see left the star thousands of years ago, a snapshot of ancient chaos. Betelgeuse, meanwhile, feels closer, its red glow a familiar sight in winter skies. If you were an astronaut near either star, you'd need serious shielding. The radiation would cook you faster than a microwave burrito. These stars aren't just pretty. They're forces of nature, their gravity and energy sculpting nearby space. In today's world, these stars are social media darlings. When Betelgeuse dimmed, X lit up with memes and speculation. From Betelgeuse is about to blow to it's just taking a nap. Astronomers use platforms like these to share real-time data, turning these stars into public obsessions. Meanwhile, telescopes like ALMA capture their wins, streams of gas and dust they shed as they age. Supercomputer models simulate their interiors, showing how fusion battles gravity in a cosmic tug-of-war. It's science meets spectacle, with every discovery fueling our fascination. These stars tell a bigger story. They're not just individuals, but symbols of the universe's cycle. Their outbursts enrich galaxies with heavy elements, their deaths seed black holes, and their light guides our understanding of stellar evolution. Eta Carinae and Betelgeuse are like cosmic billboards, advertising the power and fragility of monster stars. They remind you that even the mightiest giants have an expiration date, and when they go, they'll light up the sky. One last chuckle. If Eta Carinae and Betelgeuse were in a band, they'd be called the Exploding Giants. Sold-out shows, but a very short tour. Next, we'll explore how these monster stars impact life in the universe, for better or worse. Keep your telescope ready, and let's keep chasing the stars. You're standing on Earth, looking up at a sky filled with stars, wondering if one of those distant lights could spell doom for life as we know it. Monster stars, those colossal hypergiants, don't just shine. They create and destroy with equal ferocity. Their births forge the elements of life, but their deaths unleash forces that could wipe out entire worlds. How do these cosmic titans shape the possibility of life across the universe? And is Earth safe from their wrath? Let's explore the dual role of monster stars as both creators and destroyers, and find out if you should be worried about a cosmic catastrophe. Imagine a galaxy buzzing with potential. Monster stars are the universe's master chefs, cooking up heavy elements like carbon, oxygen, and iron in their fiery cores. When they explode as supernovae, these elements scatter across space, seeding gas clouds that eventually form planets like Earth. Without monster stars, you wouldn't be here. Every atom in your body, from the calcium in your bones to the iron in your blood, was forged in their hearts. It's a humbling thought. You're made of stardust, a gift from these cosmic giants. But there's a catch. Those same explosions and the gamma-ray bursts they sometimes unleash could sterilize a planet faster than you can say extinction event. Feel the stakes. A supernova within 30 light-years of Earth could bombard us with enough radiation to shred our ozone layer, letting ultraviolet rays cook the surface. A gamma-ray burst, even from thousands of light-years away, could be worse. Its focused beam could trigger a mass extinction, like the one some scientists think hit Earth 450 million years ago during the Ordovician period. You'd see auroras lighting up the sky, beautiful but deadly, as the atmosphere ionized under the onslaught. And here's a little cosmic humor to keep things light. Why don't monster stars make good neighbors? Because they throw the worst kind of block party. Everyone's invited, but nobody survives. Let's put this in perspective. Monster stars are rare, and their dangerous outbursts are even rarer. The Milky Way hasn't seen a nearby supernova in centuries, and gamma-ray bursts are unlikely to hit us directly. Their beams are narrow, like cosmic laser pointers, but their influence is vast. Their explosions trigger new star formation by compressing gas clouds, creating nurseries for future solar systems. They also enrich galaxies with metals. Astronomers speak for elements heavier than helium, which are essential for rocky planets and life. It's a cosmic balancing act. Monster stars give life a chance, but they also hold a loaded gun. For a historical touch, let's revisit 1987, when astronomers observed supernova 1987A in the Large Magellanic Cloud, a nearby galaxy. It was the closest supernova seen in nearly 400 years, and it gave scientists a front-row seat to study a monster star's death. The data confirmed that supernovae spread life-giving elements, but also showed how their radiation could disrupt nearby systems. Telescopes worldwide tracked the event, and it's still studied today, with its shockwaves still expanding. It was a wake-up call about the power of massive stars, even from 168,000 light-years away. Here's a quirky fact. Some monster stars might indirectly help life by clearing out cosmic clutter. Their supernovae create bubbles of hot gas that sweep away dense clouds, making it easier for new stars to form stable systems. It's like a cosmic landscaper, tidying up the galaxy for habitable planets. But if a star like Betelgeuse, just 600 light-years away, went supernova, we'd get a spectacular show, bright enough to see in daylight. But its radiation might still cause minor damage to our atmosphere. Luckily, Betelgeuse's axis doesn't point our way, so a gamma-ray burst is off the table. Now, let's spark a scholarly debate. Could monster stars be the key to life's distribution, or are they too destructive to allow life nearby? Some astrobiologists argue that their supernovae create the conditions for life by spreading metals, but only at a safe distance. Others say their radiation makes nearby systems uninhabitable, limiting life to galactic safe zones far from massive stars. This question drives research into exoplanets and galactic habitability, with scientists modeling how radiation from monster stars affects young planets. It's a cosmic Goldilocks problem. Too close and you're fried. Too far and you lack the elements for life. Feel the tension. You're on a hypothetical planet near a monster star, watching its unstable glow. Its radiation bathes the surface, mutating early life forms or wiping them out. Yet, in its death, it scatters the seeds of new worlds. It's a paradox, creation born from destruction. If you were an alien astronomer, you'd be torn between awe and fear, knowing this star could both make and break your world. On Earth, we're lucky. Our sun formed in a quieter region, far from the galaxy's monster star hotspots. Today we study these effects with cutting-edge tools. Exoplanet hunters use telescopes like Kepler to find worlds in habitable zones, checking if they're near massive stars. Supercomputers simulate supernova impacts, showing how radiation travels and what it does to atmospheres. On platforms like X, scientists share findings about galactic habitability, sparking debates among fans and researchers alike. It's a modern quest, blending astronomy and astrobiology to answer, where can life thrive? Monster stars are at the heart of it, their legacies shaping the cosmic map of life. So, are you safe? For now, yes. The nearest monster stars, like Betelgeuse, are too far to cause immediate harm, and gamma-ray bursts are unlikely to target us, but the universe is vast, and other worlds may not be so lucky. Monster stars remind us of our fragile place in the cosmos, but also our connection to it. Every breath you take carries atoms from their ancient explosions, tying you to the universe's grand story. One last chuckle. If a monster star were a gardener, it'd plant the seeds for life, but occasionally mow the lawn with a flamethrower. Next, we'll reflect on what these cosmic giants teach us about our place in the universe. Keep your wonder alive, and let's see where this cosmic journey takes us. You're standing under a star-filled sky, the vastness of the cosmos stretching above you. Somewhere out there, a monster star burns. Its light a reminder of the universe's raw power. These hypergiants, with their blazing lives and explosive deaths, make you feel small, yet strangely connected to something immense. They're not just stars. They're symbols of creation, destruction, and the relentless curiosity that drives us to explore. What do these cosmic titans tell us about our place in the universe? And why do they spark both awe and fear? Let's reflect on the profound lessons they offer and our role in this grand cosmic story. Picture yourself gazing at the Milky Way, a glittering band of light across the sky. Each pinprick of light is a star, but only a rare few are the monster stars we've been chasing. Hypergiants like Eta Carinae or Betelgeuse, whose lives burn bright and brief. Their scale is humbling. If you were to shrink the universe to the size of a city, Earth would be a speck of dust, and these stars would be towering skyscrapers, glowing with enough energy to light up entire neighborhoods. Yet, their deaths, supernovae, gamma-ray bursts, black holes, remind you that even the mightiest giants fall. It's a cosmic cycle that makes you wonder. In a universe so vast and violent, what's the point of our tiny existence? Feel the weight of that question. These stars, born from chaotic clouds and dying in cataclysms, are both creators and destroyers. They forge the elements that make life possible, scattering carbon and oxygen across space to form planets like ours. But their explosions could wipe out life in an instant, a reminder of the universe's indifference. You're caught in a paradox. Monster stars are the architects of your existence, yet they embody a primal fear of destruction. It's like standing at the edge of a cliff, awe-struck by the view, but aware of the drop. And here's a little cosmic humor to ease the tension. Why do monster stars make us feel small? Because they're the universe's way of saying, you're not the star of this show. Let's ground this in scale. The universe is 13.8 billion years old, and monster stars live just a few million years, a cosmic blink. Yet their impact lasts eons, shaping galaxies and seeding the building blocks of life. You're part of that legacy. The iron in your blood, the oxygen you breathe. It all came from stars like these, forged in their fiery cores and blasted into space. It's a connection that ties you to the cosmos, making you feel both insignificant and integral. Every time you look up, you're seeing the story of your own origins, written in starlight. For a historical touch, think back to Galileo in the early 17th century. When he turned his telescope toward the stars, he saw the Milky Way resolve into countless points of light, challenging the idea that the heavens were perfect and unchanging. His observations laid the groundwork for understanding stars as dynamic, evolving objects. Today, we know monster stars are the extreme end of that evolution, their brief lives a testament to the universe's restless energy. Galileo couldn't have imagined the scale of hypergiants, but his curiosity set the stage for our modern quest to understand them. Here's a quirky detail. Some monster stars, like VY Canis Majoris, lose so much mass before exploding that they create stellar winds strong enough to carve out cavities in space. These winds are like cosmic breath, blowing bubbles of gas that can stretch light years across. It's as if the star is sculpting its own memorial before its final act, leaving a ghostly imprint for future astronomers to study. This mass loss makes their deaths even more unpredictable, adding to their mystique as cosmic wildcards. Now, let's spark a scholarly debate. Do monster stars inspire more fear or wonder? Some argue their destructive power. Supernovae that could sterilize planets, gamma-ray bursts that could end life, makes them symbols of cosmic danger. Others see them as emblems of creation, their deaths birthing the elements and conditions for life. This tension drives philosophy as much as science, pushing us to ask, is the universe hostile or nurturing? Astrobiologists and astronomers wrestle with this, studying how these stars shape habitable zones in galaxies. It's a question that resonates beyond data, touching on our deepest instincts about existence. Feel the pull of this moment. You're not just looking at stars, you're confronting the universe's duality. Monster stars are beautiful. Their light a beacon across billions of years. But they're also terrifying. Their deaths reshaping entire regions of space. If you were a poet, you'd write about their fleeting glory. If you were a survivor, you'd pray to stay out of their blast zone. This blend of awe and fear is what fuels our drive to explore. From backyard telescopes to billion-dollar observatories. It's why we keep looking up, asking questions, seeking answers. In today's world, monster stars are more than scientific subjects. They're cultural touchstones. When Betelgeuse dimmed in 2019, social media erupted with memes and theories, from alien cover-ups to imminent explosions. Astronomers used platforms like X to share real-time data, turning a distant star into a global conversation. Telescopes like the James Webb capture their light in unprecedented detail, while supercomputers simulate their lives and deaths, letting us peer into their cores. It's a golden age of discovery, where every new image or data set brings us closer to understanding our cosmic roots. These stars challenge you to think bigger. They're a reminder that the universe is vast, unpredictable, and full of wonders we're only beginning to grasp. Your curiosity, your drive to ask why, mirrors the restlessness of these stars. They burn bright, they explode, they reshape the cosmos, and you, in your own way, are part of that story. A fleeting spark in a universe that's both beautiful and terrifying. One last chuckle. If monster stars had a motto, it'd be, live fast, die young, leave a glowing nebula. As we close this journey, take a moment to look up. Those stars are out there, burning, exploding, creating. What's your place in their story? Share your thoughts in the comments. Keep your curiosity alive, and let's keep exploring the universe together.